Characterization of nanomaterials. Nanomaterials exhibit distinct size dependent properties in the 1 to 100 nanometer range, where quantum phenomena are involved. The following articles describe the production and characterization of different types of nanomaterials, where the structural and mechanical properties are determined and discussed. In general, characterization refers to the study of properties attributed to the material experimentally. The study of nanoparticles and their properties through optical imaging is not possible. Thus, there was a necessity to find optimized technique exploiting specific properties of electron beams and X-rays. Hence, the process studying of nanomaterials features such as its composition, structure, and various properties like physical, electrical, magnetic, etc.
Why optical microscopy is unsuited for nanomaterials. Though the optical microscope is now assisted by computer-aided optical design and automated grinding methodology, glass-based microscopes are still hindered by an inevitable limit in optical resolution that arises by the diffraction of visible light wavefronts as they pass through the circular aperture of the structural aberrations of the specimen. Since the drawbacks faced are a result of fundamental physical phenomena itself, alterations to the lens and aperture design are yieldless. These resolution limitations are often referred to as diffraction barrier, which restricts the ability of optical instruments to distinguish between two objects separated by a lateral distance less than approximately half the wavelength of light used to image the specimen. Since the wavelength of visible light is 500 nanometers, object with a lateral distance of approximately 250 nanometers is only available.
The process of diffraction involves the spreading of light waves when they interact with the intricate structures that compose a typical specimen. Most specimens observed in the microscope are composed of highly overlapping features that are best represented by a multiple point sources of light. That is why discussions of the microscope diffraction barrier tend to focus on describing the passage of wavefronts that represent a single point source of light through the various optical elements and aperture diaphragms. The transmitted light or emission wavefronts emanating from a point in the specimen plane of the microscope become diffracted at the edges of the objective aperture. This effectively spreads the wavefronts to produce an image of the point source that is broadened into a diffraction pattern, which has a central disk of a finite size, but the size is larger than the original point.
Techniques using X-rays are X-ray diffraction and small angle X-ray scattering. X-ray diffraction is based on constructive interference of monochromatic X-rays and a crystalline sample. The interaction of the incident X-ray with the sample produces constructive interference and a diffracted ray when conditions satisfy Black's law. This law relates the wavelength of electromagnetic radiation to the diffraction angle and the lattice spacing in a crystalline sample. Small angle X-ray scattering is a technique by which nanoscale density difference in a sample can be determined. This means that is can determine nanoparticle size distribution, resolve the size and shape of macromolecules, determine pore sizes and much more. This is achieved by analyzing the elastic scattering behavior of X-rays when traveling through the material, recording their scattering of small angles.
E-beam based, electron beam based. An electron microscope is a microscope that uses a beam of accelerated electron as a source instead of light. As the wavelength of an electron can be up to 1 lakh times shorter than that of visible light photons, electron microscope have a higher resolving power than optical microscope and can reveal structure of smaller objects since the wavelength of E-beam is shorter. The diffraction limit is much smaller than photons, hence allowing higher resolution. based on the method used to generate electron beam. There are three types: scanning electron microscope SEM, scanning tunneling microscope STM, and the last one, transmission electron microscope TEM.